Let's look at an example. Let's say we have x, y. X is like the outcome of a flipping a coin. Let's say it can be head or tail. And let's say make it more interesting. Let's say the coin is biased, and then the let's say probability of head is 0.4. Let's say, and y is outcome of flipping another biased coin. Let's say it's also 0.4. And C, let's say, is basically the probability have getting or not probability the outcome. It can have two outcomes. Let's say it either want to see whether x and y is head tail, or like have different value. Or maybe I could write like C basically is as just 0 and 1. So 1 if like x is equal to y, and 0 if like x is not equal to y, let's say. So what will be this value like? So instead of head or tail, let me just use 0 and 1 for everything. It would be more consistent. So let's say x and y and z. We want to look at the value of z, and z equal to 0 for the case x and y, z equal to 1, x can be 0 and 1, y can be 0 and 1, 0, 1, 0 and 1. And for what is given by the setup of this problem, probability of getting both x and y is head will be 0.4 multiplied by 0.4. That will be 0.16, right? Okay. And know that like when x is equal to y, z has to be equal to 1. So therefore this is not possible. So actually this would be 0 here, but instead here will be 0.16. And similarly, if I have like both x and y is tail, the probability is 0.4 times 0.4 will be 0.36. Again, like when x is equal to y is equal to tail, c can only be 1, so this is not possible. On this side, we cannot have x is equal to 1, y equal to 1, and z equal to 0. Therefore, the probability here will be 0, and here will be 0.36. Similarly, if I want to see like what's the probability of x to be head and y to be tail, that will be 0.4 multiplied by 0.6, will be 0.24. But in this case, when x, because now x is not equal to y, z has to be equal to 0. Therefore, I should have 0.24 here, and here I should have 0 here. Similarly, I have 0 here, that's 0.24 here. So I have built a joint PMF for this joint distribution as a table. Actually, two tables here. Now we can compute number of value. Let's say we can compute what's the entropy of x. That's easy. We don't even need to look at this table here. We know that the entropy of x should be just equal to h.4 or equal to minus log 0.4 minus log 0.6, something like that. Let's look at something more challenging. What's the entropy of z? So entropy of z, we can compute this by first finding the marginal distribution of z, what's the probability of distribution of z here? We can see that like with probability upon all these four cases will corresponding to z equal to 0, right? So therefore, like the probability that z equal to 0 is basically this add together will be just 0.48, and probability z equal to 1 will be just 0.52. So therefore, z is just simply 0.48, h.48. Will be equal to something like that. Basically, minus 0.48 log 0.48 minus 0.52 log 0.52. So, okay. Let's compare, for example, what's the conditional entropy of y given x? Okay. Know that like, okay, let's just compare it like in a straightforward manner, just in a sense like we can compute this by first principle, basically thinking this as an average of like px and hy given small x, and px here, x can be 0 and can be 1, and when x is equal to 0, then that's basically these two columns here. What's the probability of y? Probability of y, okay, let me expand this first. This is a probability x equal to 0, hy given x equal to 0, plus probability y equal x equal to 1, hy given x equal to 1. Okay, so now when x equal to 0, that's these two columns here, the probability of y will be 0.16 and 0.24, but of course we know that we need to normalize it, because now in this case we only restricted ourselves to the case that x equal to 0, therefore we should normalize it by dividing to the probability of x equal to 0, that's basically, or we can simply sum these two together, will be just 0.4, right? And therefore this will give us the probability is basically 0.4 and 0.6. So therefore, like hy given x is just h.4, probability x equal to 0. And when x equal to 1 will be these two columns here, the probability will be like 0.24 and 0.36. Again, I need to normalize this to 1, so I should over the probability of x being 1, that's basically 0.6, that's 0.24 plus 0.36. And again, I should get 0.4 and 0.6. So I have h.4 here. So therefore, like, of course, I can pull this h.4 here, and it's just probably x equal to 0 plus probability x equal to 1. And of course, this probability will sum up to 1 is just equal to h.4. Of course, like, we went through a whole lot here, but we can write it out right at the beginning, because by what we define in the problem, we have assumed that x and y are independent. So therefore, like hy given x right at the beginning, we know that like it should be just equal to hy. Or like if you look at it here, because y is independent of x, no matter what parameter if you think of x as a parameter, what small x is equal to, it doesn't change the distribution of y. Therefore, hy will be always the same. It is always the same as the original y. So therefore, like hy will be just equal to hy given x. And so let's compute a bit more challenging. Let's say, how about z given x? So z given x will be, again I can write x as this xps z given small x here. So it will be like px equal to 0, z given x equal to 0 plus p x equal to 1, z given x equal to 1, and px equal to 0 is, as we can see, is just equal to 0.4. That's this plus this plus this plus this. It's just equal to 0.4. Z given x equal to 0. And x equal to 1 is just equal to 0.6. Z given x equal to 1. And what should this z given x equal to 0? It will be similar to what we did here for computing hy given x equal to 0. But in this case, it will be more interesting. It won't be trivial. For x equal to 0, basically this 4 entries here, this 2 column here, the probability of z equal to 0 is 0.24 and 0.16. And of course, I need to normalize again. So this should be like pz equal to 0 is equal to 0.24 over 0.4, and this is equal to 0.16 over 0.4. So this will give me 0.6 and 0.4. So therefore, this should be just equal to 0.4. And when oops, actually, in this case, still be trivial because okay, let me finish it. And I will explain why it's still trivial in this case. Z is equal to, for x equal to 1, it will be these 4 entries here. And the probability for z equal to 0 is 0.24 and z equal to 1 is 0.36. So we need to divide it by the probability of x equal to 1. So it's 0.24 over 0.6. That's basically give a 0.4 here. And this is 0.36 over 0.6. This gives a 0.6 here. So it gives us the same thing again, like h.4. So again, like this, in this case, is actually just equal to h.4 here. Why is that so? Because in this case, there are trivial case because we have x and y are independent, and z is like a function, or like we can think of like z is just a binary sum of x and y. It's equal to x plus y here. And but if you think of like given x, then this expression x plus y, this x here will be a constant. For the if we compute a Shannon entropy of some variable plus a constant, the constant can always be low because it only shifts the distribution. It doesn't change the distribution itself. Therefore, like this will be just equal to hy given x, and we already know that hy given x is just y and x are independent, so it will give me hy again. So okay, I at the beginning I thought this may not be a trivial question, but yeah, we don't actually need to go through these steps, and we can go through quickly and know that like h z given x is equal to hy, therefore is equal to h.4. So let's see if we have something that's less trivial. So and by the way, so what is ixy? Ixy will be equal to hy minus hy given x, and we already know that hy given x will be just equal to hy, therefore ixy is equal to 0. And that's expected because when mutual information is equal to 0, it basically means that there's no overlapping of these two random variables. So therefore it's supposed to be independent. There's no overlapping in outcome. You can not exactly outcome. In terms of Venn diagram, there will be no overlapping, and you can think of that they are independent. And let's see, how about ixmz? That will be equal to hz minus xz given xy. So what is hz we have computed? Hz is equal to h.48. hz given x is equal to 0.4. It will be simply this. So how about y given xz? Well, this is just equal to 0, because if you think of that given x and z, y is completely determined, because z is defined as basically c is really equal to, although if I didn't write it out, but it's really equal to a deterministic function that's basically bitwise addition between x and y. So therefore, like since z is equal to x plus y, we can also think of like x is equal to y plus z, because we can add this on both sides. This will get cancelled. We can, I can for that both left hand side and right hand side add the y here, but on this side, this bitwise addition of y twice, this will get cancelled. So I have x here only, so I have x equal to y plus c here. And similarly, I will have y equal to x plus c also. So in any case, since y is equal to x plus c, so therefore like this is a deterministic function of x and z, therefore will be no information if we already know x and z. So finally, let's compare, let's say, the conditional mutual information of x and y given z. This will be equal to hy given z minus y given x and z, right? So we already computed this one, that is equal to 0. Let's see if we have computed y given z. Actually, I think we didn't. Let's see. But I know the variables are symmetric. Actually, we have computed z given x is equal to h.4. Therefore, I know z given y will also be equal to h.4. So let's see if we can from here to get to here. So this will be equal to h y z minus h z, right? And on the other hand, this h y z here will be equal to h y plus h z given y. So therefore, like, we don't need to go through from scratch again. So basically, we have hy given z is equal to hy plus hz given y minus hz here. So therefore, like, it should be equal to hy, I know, is equal to h.4, right? Yeah, hy, I didn't want hy, but hy is equal to hx. So hy, okay, it's actually here. Hy is equal to h.4. Hz given y is equal to h.4 again. And hz is equal to h.a for a, I think. Right? Computed earlier here. Yeah. And so minus 0. So okay, now this. So basically, it's just equal to this. So I guess hopefully this this example will get you a little bit more familiar with the definition. Okay, I guess next time I will talk a little bit some property of this information measure. In particular, I'll show that all of this bigger than 0. To show that it's actually it's usually convenient to introduce something so-called known as the relative entropy or Kullback-Leibler divergence. That is basically a measure of two distribution. So the divergence is basically when we have like Kullback-Leibler divergence of px between px and qx, this two distribution will be just equal to px log px over qx. So sometimes you can think of this as a measure of how difference of these two distributions, but know that this is not really some kind of measure people typically think of that is commutative, in the sense that this usually we think of measure from a measure from point A to point B will be the same from point B to point A, but this kind of measure here is not really exactly a measure that is not commutative. For in the sense that you can see apparently dpxqx is not equal to dqx px. So next time we'll show that this is positive, and this is a pretty useful expression, equation, inequality I should say. It's pretty useful inequality in showing number of information measure inequalities.